Hello everyone and welcome back to another video of the Hidden Quantum Champions. You see me talk a lot about quantum hardware as in sensors, communication and also computing hardware. But in order to make things actually useful, to build applications like solutions on top of this hardware, there's always also the component of software needed. And today's video is going to be about software as we look into a company called BlueQubit that is making software for quantum computers. And if you want to know what their software is all about, why we actually need this kind of software and why maybe Qiskit as an open source, just one open source example, might not be enough, and where companies like BlueQubit actually find their niche or find their application and why this even exists, then you are exactly right for today's video, because we are diving deeper into BlueQubit and what their company and their software is all about. And with that, let's get started right away. So before we get started, as always, make sure to get yourself something to drink, because it's always important to stay hydrated. And as well, the other component, if you are interested in software companies in the quantum space, let me know down in the comments below. I'm very eager to also do more videos about the software side of things if this is interesting to you as well. Now let's get started. Let's look at their website. Here it says Enterprise Quantum, supercharge your R&D with BlueQubit. Our enterprise, defense and academics customers implement gate-based quantum algorithms today using our quantum software as a service platform on their hardware of choice. Now, very quickly, one step back, what is gate-based quantum algorithms? So just as a note, there are different machines that can be used to do quantum operations out there today. One of the very early players in the quantum machines market is, for example, D-Wave. They are making what is called an optimizer. So it is basically using quantum annealing, which is one specific method to run optimization algorithms or to run a specific kind of optimization algorithm on their machine, which might be interesting for, I don't know, logistics problems and other types of problems. We've also talked more about that in the dedicated video about D-Wave that you find on this channel. Now, this is not a gate-based system. It is using this very specific technique of the quantum annealing to solve a very specific type of problem classes. The other category of machines that we are seeing right now is the gate-based algorithms and gate-based quantum computers. And very similar to classical computers, we are talking about gates as in fundamental operations. So if you think about a classical computer, you have bits, ones and zeros, and you can run operations on them, like a logical AND, a logical OR, a NOR gate. So these are all gates that you can basically run, and they might add two bits to each other or subtract two bits from each other. And based on these general operations, you can then build the whole logic that basically runs underneath our operating system that is doing all the calculations, can build very simple machines that can add functions to each other, and then you can build basically from there on. But the fundamental, let's say, logical units are the gates, and they are made out of transistors, which are what your chip is on. There's an analogy for the quantum world. So we have the quantum bits, or qubits for short, and they can also run different types of fundamental gates on them. You can, for example, run a Hadamard gate. As just one example, there's also CNOT and other gates that can basically be used to build up a fully functional quantum computer. So there's a basic set of logic gates on which you can then basically build all the relevant algorithms. This is what is called gate-based computing. You're taking multiple of these gates and stacking them on top of each other such that they become or form into a quantum algorithm. The other component is on your hardware level, on your hardware of choice. So there are different hardware systems out there, and we will see later on when we are looking at this page, I think in a couple of seconds, what hardware they are referring to, what is the hardware that their platform is running on today. But first we see this trusted by part here, which is listing partners and other players that they work together with. You see IBM here as a big brand, or AWS and NVIDIA, but we also see academic players like Stanford University, industry players like Honda and Guidewire, and then we see Continuum as a, let's say, more quantum player on the or pure quantum player on the list. Of course, others are also quantum players, but Quantinuum is, let's say, a quantum native one. Now, connect to IBM Heron and Quantinuum H2 QPUs. QPU is a quantum processing unit. Unlock the full potential of quantum computing with BlueQubit. Our platform supports the best quantum computers, IBM Heron and Quantinuum's H2 QPUs, enabling you to run thousands of gates and powerful utility circuits seamlessly. About these two hardwares, right, we see here IBM FATS. IBM Heron is IBM's latest, most powerful quantum processing unit with 156 qubits, a 1 qubit fidelity of 99.97 and a 2 qubit fidelity of 99.7%. The fidelity basically has to do with the accuracy. Today's qubits, we call them physical qubits, and we call it the NISQ era, the noisy intermediate state quantum systems era, means today we build those qubits physically on the chip. In the case of IBM, they use superconducting qubits, and these qubits, they are little circuits that sit on the chip, and there's always, let's say, some loss of accuracy because of various different reasons that accumulates over time. So that is being expressed in the fidelity. There's the 1 qubit fidelity that refers to single qubit operations, and the 2 qubit fidelity that refers to 2 qubit operations, like when you try to entangle 2 qubits with each other. Those metrics are very important because over the time these accumulate and lead to what we call decoherence. So basically you're losing the quantum information. It's not very easy to actually correct for those because you're entangling so many of these systems. So basically your error is spreading across the whole system, across the whole architecture, which is different from a classical computer where every single bit is its own entity. Here they become a collective entity due to the effect of entanglement. And also because there's the non-cloning theorem, it's not so easy to just copy information, save it elsewhere, and then compare these two bits to each other, because whenever you measure the system, you're losing information. So it's very difficult to correct for these things. There's a whole another research area called quantum error correction where this is being treated, and that then leads from the physical qubits that we have on the chip to what we call logical qubits. These are error corrected qubits where in the background this error correction is running and making sure that your information is not getting lost but properly being restored or being corrected upon. So this is the area, this is the difference between the NISQ time and the error corrected quantum computers. Now, these fidelities that we are seeing here are, let's say, probably among the best in class. And then on the other hand, here we see the Quantinuum H2 system, which works in a different way. And there we see the fidelities are much higher. So here you can see it's 99.97 for single qubit, where we had 99.97 before. Here it's 997. And for the 2 qubits, we see 8.5, and it used to be 7 in the other case. So that's the advantage of those systems. The disadvantage is the number of qubits is limited. So here we are at 56 qubits at the current latest state of this H2 process. If you want to know the difference of how these architectures work, check out the dedicated videos both for Quantinuum and, well, I don't have one for IBM, but you can basically look for superconducting qubits and you will find it. And then you can compare them to each other, like how they actually work and how the quantum information is being implemented. Now on the testimonials, you see those different players that were mentioned above before. We look at Guidewire for now. Here it says Guidewire and BlueQubit partner together in an endeavor to translate real-world challenges into finding practical applications for quantum computers to address prevalent issues in P&C insurance. As an example, BlueQubit assisted Guidewire in executing a 41-qubit 16 terabyte simulation to address the capital reserve challenge. Then we see down here, access the best quantum resources, so latest QPUs and emulators. We've seen those one before. We also see here IonQ listed and Rigetti as an example. Then we see Quantum Monte Carlo, so risk analysis, VAR, CVAR, and deviative pricing. We've also talked about these specific ones before. There are also quantum random number generators that can be used for Monte Carlo or quantum-based Monte Carlo simulations. And then there's the quantum AI solutions, so portfolio optimization and fraud detection, probably using quantum computers in the loop as QPUs. Then we see here early adopters will benefit the most from the quantum advantage, and the call to action to start today and get quantum ready. We also see a hackathons part here, so you can participate in hackathons, and of course there's a call to action here to participate in a challenge and win prizes like a quarter of a Bitcoin. The challenges are, I guess, explained here. So peaked circuit challenge, peaked circuits. Right now is one of the challenges that they have. It says participants of the BlueQubit Quantum Hackathon will receive special quantum circuits, peaked circuits, where each circuit sets up a specific quantum state. Hidden within that state is a single bit string that appears with high probability. Our mission is to find the bit string. And then, down here you see the partners that are participating. A lot of them we've already featured previously, at least the quantum companies in the Hidden Quantum Champions. And then, of course, you also see other industry players and academic partners. So peaked circuits in a nutshell. Peaked circuits are pre-structured quantum circuits with a non-uniform distribution of measurement outcomes. What are peaked circuits? They are designed in a way that one particular bit string has a higher probability than others, for example, order of 1, as opposed to exponentially small amplitude. Our challenge is to identify the peak bit string in the distribution. Who created them? They were introduced by Scott Aronson as a way to achieve variable quantum advantage. Carefully crafted peaked circuits look like random circuits, like the one used by Google in their benchmark, that would take supercomputers septillion, so 10 to the 25 years to replicate. However, unlike random circuits, peaked circuits are much easier to verify. All you need to do is to run them on a quantum computer and verify you get the correct hidden bit string. BlueQubit Quantum Hackathon. This quantum hackathon aims to test the skills of quantum researchers and enthusiasts in how well they can use quantum computers and simulators to crack peaked circuits. Then about the company itself, there's also something stated here and some frequently asked questions. Now let's quickly peek into the platform that they actually offer. You can already see here that they not only offer a platform but also a programming environment, because that looks very Pythonic from what I see here. It says BlueQubit's quantum computing software. Design, simulate, and run quantum circuits from your browser. No quantum hardware needed. It's the simplest way to run quantum programs on CPU, GPU, and QPU with a star. Get started, and then you see here this Pythonic access. It says quantum computing software features, integrated quantum simulator, hardware execution via cloud, and then versioning and experiment tracking. So on the simulator side, run quantum programs on a high fidelity simulator with up to 40 qubits. You can debug and validate your circuits in a realistic environment before sending them to real quantum hardware. Then hardware execution via the cloud. Get access to quantum devices directly through your quantum cloud computing software, through our quantum computing cloud software. No need for special hardware. BlueQubit connects your circuits to quantum processors in real time, and then versioning and experiment tracking. Keep track of changes in your quantum circuits with version control and drop metadata. You can review past iteration, compare results, and go back to previous states whenever needed. So this is basically the same infrastructure that we have in today's, let's say, modern or more modern machine learning environments, where you're not just randomly shooting stuff in different directions and then never really figure out which parameter you used, but you have a smart environment that is basically tracking those things for you. And there's this logical thing where you start with a simulator and then move to the cloud so you don't burn resources for unnecessary and experimental stuff. So basically it is a very solid and fundamental layer that takes care of all the work around the quantum computing that you need in a modern R&D and lab setup environment, so that you don't have to code all of these things or set these infrastructures by yourself. So how it works, first step is you create an account, you design your circuit, then you test it in the simulator, you run it onto real quantum hardware, and finally you visualize and interpret your results, which they also have tools for. And we can see this over here. So we see the quantum circuit, which I was talking about before. So you see the different gates, like the Hadamard gate applied here, or some rotation gates as well. You see the state vector probabilities of your outcome down here for the different qubit combinations and the probabilities. So if I zoom in, maybe not. Yeah, you can see the probabilities and the different bit outcomes. And then, yeah, down here, I guess you also have the different jobs that are being managed by the software as well. Access BlueQubit's cutting-edge quantum algorithms. So there are also algorithms that they already provide that you can work with. There's quantum data loading, quantum AI and machine learning, and then quantum enhanced sampling. When it comes to data loading, it says unlock powerful quantum capabilities with our suite of production-ready algorithm libraries. Then there's the machine learning one over here, and the enhanced sampling over here. Refine your probabilistic models using our next-gen quantum MCMC techniques developed with DARPA. True quantum randomness will let you go beyond classical limits. Then why choose BlueQubit? First of all, it says scalable for growth. So BlueQubit offers flexible pricing plans and infrastructure to support personal projects, collaborative research, or production scale quantum development. The platform is built to adapt to your workload and grow with your needs. No hardware needed, so run quantum algorithms without investing in expensive infrastructure. BlueQubit provides access to real quantum processors via the cloud. Just log in, build your circuit, and execute it on real quantum processors, all through your home or office computer. And then finally, free plan available for all the makers in this community that are listening still until this point of the video. Explore quantum computing at no cost with a 33 qubit CPU simulator and basic circuit features. The free plan includes access to tutorials, simulators, and visuals, ideal for beginners, enthusiasts, and early stage developers looking to test ideas. And if you want me to test this out, or if you want to do this together, we can also think about live sessions where we code together with this. Let me know down in the comments below. I'd be very interested in your opinion on that. And if you want me to do this, I'm happy to also dive deeper into the technology of BlueQubit or any other platform that you might be actually interested in. I'm always calling you for action on this. I haven't done it in a while, so I thought I point it out again. Here we see the pricing. So there's the free plan, as mentioned before, which goes with 100 jobs max per day. And this hybrid mini setup here, there's a $20 per month license as well, and then there's this $100 per month license, which is premium. Okay, and then we see the FAQs down here. Now let's quickly also check out the other sections here very briefly. So there's a blog as well. I'm recording this video in April of 2026. You see the latest blog article that is mentioned here is from January 2026. So I'd say reasonably up to date. It says quantum advantage you can actually verify inside peaked circuits. So I guess that's according to this challenge, this hackathon that they have up and running, but there are many other blog articles available here as well. And there's also some research section down here, which covers research articles, I guess, that they are involved in. The latest one is from December 2025 saying convergence of sample-based quantum diagonalization of a variable length corporate chain. Okay, that sounds very researchy. Now, finally, as always, let's quickly check out the company and the team, right? So here it says meet our team. The BlueQubit team is where advanced quantum R&D meets excellent software infra. So they're on the software infrastructure side providing layer. I talked about that before. Here we see the co-founder team, but you also see that there's like engineers already involved, head of engineer, quantum R&D engineers. You see there's sales development already on board. software development, of course. You have quantum engineers as well. There's an advisory board mentioned here as well. And that's, I guess, the overview of BlueQubit. With that, I'm also finishing already upon today's video. I hope you liked it. If so, and if you stayed all the way to the end of this video, please make sure to give it a thumbs up. I'm looking forward to see you in the next one. Until then, bye bye.